Good morning. Yeah, I hope all of you healthy today. Yeah. So last week we don't have a class, yeah, through Zoom, but I have uploaded some videos for you to watch, yeah, so that I expect that you have seen the video. Have you?
Yes, ma'am.
Okay. What about the others?
Yes, ma'am.
Excuse me, ma'am.
Yes.
May I ask a question from the video, ma'am?
Yes, of course. Yeah, Fifi.
In slide 30, I still confused how we get
Which one is that?
slide 30 about Simpson 1/3 rule.
Here is not the same. About finding the error, yeah? Is it?
Yes, ma'am.
Okay, so it's about finding the error of the Simpson method rule. Okay. So that should be I will try to share the slide here. Okay, is this the slide that you mean?
Yes, ma'am, but the example one.
Example one. Oh, the example here. Here.
Yes.
Okay. Okay, so the question is about the Simpson method rule, yeah. So the third method here, yeah.
Yes, ma'am.
Okay, so here to find the value of the fourth derivative, yeah. To find the value of the fourth derivative, it means that we have to find the derivative of the equations, yeah, the fourth derivative of the equations. So that if we look at here, we have these equations, yeah. So that we can find the first derivative, yeah. So that will be 25 minus 400, yeah. So I will try to write it down here. So if we calculate f1x, the first derivative of x, of the function, yeah, so that will be 25 minus 400x plus 675 times 2, yeah, so that times 2 times 3 squared x minus 900 times 4, that will be 3600 x to the power of 3 plus that will be 2 0 0 0 x to the power of 4, yeah. So that when we find the second derivative, so that will be minus 400 plus, so this is multiplied by 2, so that will be 1350 times 3, so that will be 4050, so this is correct, minus that will be 10,800 squared x plus 8,000 x to the power of 4. Yeah, so that will be 8,000 x to the power of 3. Okay, so this is correct. And then to find the value here, so we can do the integration from between the limits from 0 to 0.8, and we integrate it to dx. Yeah, and then we divide it into with 0.8 minus 0, so that if we want to find for the third derivative, so we will calculate the third derivative here. Yeah, so that will be equals to 450. Yeah, 450 minus that will be 21.6. Yeah, x plus that will be 24,000. Yeah, 24,000 squared x. So that the fourth derivative will be minus 21,600. Yeah, plus 48,000 of x. Yeah, and then we do the same thing as this one. So we can find the average of the fourth derivative in the interval. Yeah, so that will be from 0 up to 0.8, where the function is minus 21,600 plus 48,000 x, and we do the integration up to dx, and this is divided by 0.8 minus 0. So with this, if we do the integration, so that will be minus 21,600 x. Yeah, back again to the value before. Yeah, so that is minus 21,600 x plus 24,000 x squared, and this is from the limit between 0 up to 0.8. So if we insert this value of 0.8, so then we have 2160 times 8. Yeah, so if we insert that 0.8, can you help with the calculation? So that is multiplied by 8. Yeah, 4, so that will be 48, 8 to 12. Yeah, minus 3,240 plus we have here times 0.8, so that will be 22,400 times 8, so that will be 2 times 8 is 16, so that will be 19,200. We multiplied again with 0.8. Yeah, so multiplied with 8, so that will be 619 times 8, 72, 73, 7, 15, 360. Now that is minus 3,240. So that will be 20. And that will be 1. That will be 12. Yeah. So that should be divided by 0.8. Yeah. Is it? So that should be divided by 0.8. Where is it? So that is should be 12. So the value is not the same. Yeah.
Yeah, it's not same.
Yeah, should be 12,120 divided by 0.8, isn't it? Now you can check that again. So what about this one? Have you tested with this one? Is it correct?
I have not, ma'am.
Okay. Okay. I will check again. Yeah. I will check again to make sure that yeah, if there is a mistake in the calculation, so this value should be corrected. Yeah, so this value should be corrected. But in general, that is how to calculate for the value. So this one as well. Yeah, so this one multiple application. The fourth derivative is also similar as well. And this one is also similar as well. So we will try again. Yeah, I will check again. Yeah, to make sure that this calculation is correct, but it's used several times. Yeah, so I will check it again. Yeah, and see whether this is incorrect. So I will let you know again, inshallah. Yeah, so I need to check the value first, but it should be calculated like this one. Yes, because we want to find the average of the fourth derivative in the interval. So that will be the same formula in calculating this. Yeah, but we have to find the fourth derivative first, and then we do the average by doing the integration and then divide it by with the interval length. Yeah, it should be like this. But yeah, I will check again why the value is not similar to the calculation. Yeah, so I will check that again. Okay, I will make note on that.
Excuse me.
Yes.
I want to ask about I still confused about the difference between f derivative with f bar derivative. What is the difference, ma'am?
Okay.
And the calculation, why the calculation is include the integral there? I still doesn't know about that.
Yeah. Okay. So here is a calculation of the approximation of the error. If we don't have the true value, yeah. So in this case, we have the true value, so that we can directly calculate the true error. But in some case, we don't have the true value. So in that case, we can approximate the error with this value, yeah. So that will be minus 112 times the average of the second derivatives multiplied by b minus a to the power of 3. Yeah. So this is an approximation for the error. Yeah. So when we want to calculate the order of the error, yeah, when we want to calculate the order of the error, so that we can calculate by we can approximate with this value, and the difference between the second derivatives here with the sign with bar here. So bar here means average, mean, yeah, the mean value. So that if we want to find the mean value, yeah, so that we can find it by finding the integration of the function. Yeah, so that will be the area underneath this curve, for example. So this is the curve, this is the equations for the second derivative. So this means that this is the curve for the second derivative. So to find the average, we can do the integration and then divide it with the interval length. Yeah, with the interval length. So this is the difference. So with bar sign here, it means that this is the average. Yeah. Okay. So yeah, so that is to answer your question, Sultan. Yeah.
Oh, okay, ma'am. It's very, very clear, ma'am. Thank you, ma'am.
Thank you too, ma'am.
Okay. For Fifi, I will check again, yeah, for the calculation to make sure that, to calculate again the correct value. If not, so that should be corrected. Yeah. Thank you. Okay.
Thank you, ma'am.
Yes. And what about the others? Any questions on this? So all of you have seen the video, yeah?
Yes, ma'am.
Okay. So no question on that. Okay. If there is no question, so I will continue to another method of integration. And this method is actually based on the previous method that we have learned. So in summary, what we have learned from the videos is that we have basically three methods. Yeah. So the first method is the trapezoidal rule, in which we approximate the area underneath the curve with a trapezium. shape, yeah. And then we have Simpson-Walter rule, in which we approximate the function, the real function, with the quadratic equation, so that we can find the area under the quadratic equations. And with Simpson-Walter Simpson 3-8 rule, it means that we approximate the real function with the third order equation or cubical equation, so that we can find the area underneath. And we can also apply the multiple segments for each of the method that has been discussed. Yeah, so using any of these, we can apply multiple segment. And please be careful that because Simpson-Walter rule here requires at least 2 segments to obtain the equation. So that means that if you want to apply the multiple segment for the Simpson-Walter rule, so that there is a special requirement, yeah, so that the requirement is that this can only be used, yeah, if you want to use that with multiple applications, so multiple segment, so this can be used only with even number of segments, yeah, only using even number of segments. So for example, if you have 9 segments, so it means it's not possible applying the same segment with multiple Simpson-Walter rule, yeah, so that we have to combine with other method as well. Okay, so this is about the 3 methods that we discussed. Now we will go on chapter 22, which is about the integration of equations still, but we will talk about one method here, which is a further improvement for the trapezoidal rule. So we have seen before that the trapezoidal rule is very simple, but the level of the accuracy is quite low because it's only using a linear line or a trapezium shape. So that we want to increase the accuracy of the trapezoidal rule, yeah. So we see here that if we have a trapezoidal rule, so that we have a with a subinterval h, that will give an error of the order of h squared. Yeah, so this is an error. So that if, for example, we want to increase to higher order scheme, so that we can combine 2 trapezoid, yeah, which is estimated at the interval h and half of h to get a better estimate. So what does that mean? For example, we have a calculation, yeah, with delta h. For example, we have a function like this one, in which we have fx and x here, and then we want to integrate from a to b, yeah. When we want to integrate from a to b, so that here we can apply multiple segment, for example, here. Now, say we use 3 segment like this one, in which for each of the segment here we have h, yeah. The interval length for each of the segment is h. So that with this, we have the calculation of I, which is this one is called I h1. In its h1 here is equals to h. So we have the calculation of the error. So that will be I1 plus I2 plus I3. Yeah, so that will be the total. So if we have, for example, we have 1, 2, 3 segments, so that the total integration area with the length of the segment of H1, which is equals to H, so that will be equals to I1, I2, and I3. And then we do the second calculation, which is the integration with the length size of H2. And the length size of H2 here is half of the initial length that we use. So if we use previously H1 is equals to H, now H2 is equals to half of it, so half the size of it. So that it means we now use the segment which is twice of the initial. Yeah. So previously we have 3 segments. Now when we use the interval length is half of it. So it means that we have more segment. Now we have twice of the segment of the previous. So that we have I1 plus I2 plus I3 plus I4 plus I5 up to I6. So twice the size of that one. Yes, twice the calculation of the previous one. So that if you look at each of these, yeah, so the difference is only the number of segments. So it means that the order of the scheme is similar. Yeah, it's still lower order scheme, but we're applying at different number of segment. Now to get a higher order scheme, so that we can combine this one, yeah, so this two lower order scheme, such as this one, yeah. So we calculate the new integration that will be approximated by 4/3 of the integration area calculated with the interval length of the segment of H2 and minus 1/3 of the integration area, which is calculated with the interval length of the segment is equal to H1. Yeah. So it means that we combine uh, the last segment, the calculation of the integration with less segment, and the integration of the calculation with more segments. So we combine both, and then when we do this calculation, so that we have a higher order scheme. Yeah. So this is basically the calculation. Yeah. So that if we want to obtain the higher order accurate scheme, so that we combining each of the calculation for the integration area with different H value. Yeah, so that we can construct a table like this one, in which the first one here is we see here that we have R00. So the first here, yeah. So the first here is denotes that this is the number of segment that is used. Yeah. So this is the number of segment that is used. So that, for example, we have 0, 0 here, R00. It means that this will be 0, n is 0. Yeah. So that will be 1. Yeah. So 2 to the power of 0, that will be 1. So it means that that will be only a single application of the trapezoidal rule. And if we use n is equals to 1, it means that we use 2 segments. Yeah, so this is only 1 segment or a single segment. 1 segment, sorry. So we have only 1 segment. And then we have the calculation here of 2 segments. And then we have here 3. Oh, sorry, twice of it. So that will be 4. And this will be 8 segment. Yeah, so that we calculate the integration area with different number of segments. And then afterwards, we can calculate the higher order scheme. Yeah, we can calculate a higher order scheme by combining the value, yeah, between the less segment with the more segments. So this, the result here will be of higher order. So this is the calculation derived from. Yeah, so that if we look at here, so that if we want to have higher order scheme in which we have previously when where we have the first order the second order error here, which is for the trapezoidal rule. So that combining these two methods here, so we end up with a higher order scheme, which is the error level now becomes fourth order. Yeah, fourth order. So how to combine that? So that we combine the new integrated area will be 4/3 of IH2. So this is IH2 minus 1/3 of IH1. Yeah, so this is what is performed in the Romberg method. So we simply combine together, yeah, the value from the lower order scheme with different number of segments, and then we will obtain the higher order segment. Again, we can combine as well here. For example, we want to use here is 2 number of segment, and then we want to compare with 4 number of segment, for example, here. Yeah. So that here we can find the new value, yeah, which is R21. So R21 will be 4/3 of R20 minus 1/3 of R10. Yeah. So that will be the higher order integration value, yeah, with more number of segments. And then if we want to increase further to 6 order accurate, so that we combine the value here, R21 and R11. Now, how to combine that? Because now we want to get to a higher order, So not the same to the fourth order, so that the equation will be different. So when we calculate R22 here, so that will be equals to, so this is a correction, yeah. So this should be 16 over 15. So please correct that, yeah, as well as in the book, yeah. So this should be 16 over 15 IM minus 1 over 15 IL. So which one is IM and IL? So IM here is the number, the value which using more, yeah, more segment minus 1/15 of the integration using less segment, yeah. So that if we calculate this one, so that the value of R22, that will be equals to 16 over 15 IMM, which is R21, R21 minus 1 over 15 R11. Yeah, so this will be the calculation. Again, if we want to increase to higher order, so that we have a 0, the order will be of the eighth order. Yeah, the error will be eighth order, so that we can combine this value, yeah, together. So that to calculate the new area, so that will be 64 over 63 times the integrated area of more segment, which is R32, minus 1 over 63 of I using less number of segment. So that will be R22. Yeah. Okay, so this is how to get a more accurate result, yeah, to the higher order level. Okay, so we will try here. Okay, so for example, we have this graph. We have x squared, yeah, in which this is 0 and 1, for example, like that one, say. And then we have positive, so probably like that, yeah, the curve. So like that, so that we have fx and x, yeah. So if we have this graph and we want to do the integration here, yeah, so this will be the integrated area. So that now the first step is to use h is equals to 1. So directly b minus a, so only 1. So one segment. So then we do the calculation of the triangle here, or the trapezium here, or similar to triangle in this curve. So that will be half of 0 plus 1. Yeah, so that the result will be 0.5. And then we divide it into two segments. So this is the first segment, I1, and this is the second segment, I2. So that when we have h now, the step size or the interface size now becomes half of h, half of the initial here. So then when we do the calculation, so that we have the calculation of the first area and the second area, so that will be 3/8. So this is the value. So that how to calculate this one, so the new area here will be, again, we look at the equation, that will be 4/3 I with more segment minus 1/3 of I with less segment. Yeah. So that we continue here, we see that it will be 4/3 of the value which has more segment. So the integration area with more segment is this one, minus 1/3 of the integration area with less segment. Yeah, so that we have here, so that will be, what is the value here? So that will be half minus so that will be 4/3 times 3/8 minus 1/3 times half. Yeah. Okay, so this is correct already. So that when we multiply that, so that will be 1/3 of half. Yeah, so that will be 1 times half, so that will be 2. So that will be 1/3. Yeah, correct. So that will be 1/3. Okay, so this is how to calculate the integration area. Yeah, so it means that when we have this value, so this is the integration area. So this is at the order, the order of h to the power of 4. So fourth order error. Yeah, fourth order error. So this is the Ramberg method. So we can increase the order of the accuracy, yeah, the order of the accuracy by combining two method, yeah, which is the trapezoidal method, to integration using lower order accurate scheme. Yeah. And then again, we can further obtain. So this is h to the 4 square. Yeah. So second order. Sorry, this is second order. So this is fourth order, and we can extend to sixth order. Yeah. So when we want to extend to sixth order, it means that we have to find the area using more segment. Yeah. So that if we previously calculated with one half, so that for this one, this should be calculated with h is a quarter. Yeah. So twice of that. So this is one segment, this is two segment, and this is four segments. So with four segments, we have h now divided by 4. So that now we calculate the result. So that will be 11 over 32, yeah, with multiple trapezoidal rule. So this is the value. So once we have this value, so that we can calculate now this value, yeah, in which the higher order value combining 4 segment and 2 segments. So that will be 4/3 times 11 over 32 minus 1/3 times 3 over 8. Yeah. So that we want to calculate the value here. So that with this one, this will be 8. Yeah, is that correct? Yeah, correct. So that we have here will be the same. So that we have 11 minus 3. So 11 minus 3 is 8. So 8 over 8 is 1. So that we have 1/3. So this is correct. Yeah, 1/3. So we error, yeah, for this calculation, and we see already that the value is the same, either using by combining the 2 segment and 1 segment, or when we combining 4 segment and 2 segments. So this means that this is actually is already the same result. Yeah, but we can further increase it to 6th order. So if we want to use the 6th order equations, so that we combining this IM with IL, yeah. So the calculation here will be equals to 16 over 15 of the value here. Yeah, so IM is 1/3, which is the bottom, more segment, minus 1 over 15 times 1/3 as well, because the value is the same, 1/3, so that the value will be constant, 1/3. Yeah. So with this, we have, this will be the result for the 6th order accurate or 6th order error. Okay, so this is a Romberg method. Yeah. Any question?
Not yet, ma'am.
Not yet, ma'am.
All right. Okay. So yeah. So with that, we can continue a bit on Gauss quadrature. Yeah. Gauss quadrature is another method in which we adjust the position, yeah, of the line. Yeah, so the points that is used to create the line is now adjusted. Yeah, so that here we have a strategy, yeah, of positioning any 2 points Okay, so with Gauss quadrature, we put a new points, yeah? So we use 2 points on a curve to define a straight line that would balance the positive and negative error, so that the area under the straight line will have a better estimation for the integral, yeah? So this is basically still using trapezoidal rule, yeah? Still using trapezoidal rule, but the points that is used, yeah, it's not the point that we use as a limit, yeah, from A to B. So that we see here that, for example, we have A here, the uh, the trapezoidal that we learned before, yeah, in which if we want to integrate from A to B, so that we use the point of A and B directly to get the linear line. Yeah. So with Gauss quadrature here, we don't use the value of the limit here as the point to obtain the linear line, but we choose another point inside, yeah, another 2 points inside, in which this will balances the positive and negative difference. Yeah. So for example, if we have, this is the limit of A and B, so this is the value, we don't connect that directly, but we choose another point here inside in which this will balance. Yeah. So we know that this will be of underestimate the area in this region, but here will be yeah, so this will be overestimated and this one will be underestimated. So the total area, when we calculate that one, the difference here, so that will be approaching to the real value. Yeah, that will be approaching to the real value. So this is what perform in Gauss quadrature. So that it means that we have to find a new point, yeah, a new points inside the area, yeah, which is x0 and x1. Yeah, so it's not the limit again, yeah, to get the linear line, but we use another points. Yeah, we have another 2 points. So that when we replace the integration here with a function, yeah, in which now this function using 2 other points, so that we have several unknowns here. And the main important to solve for the unknowns here is to minimize the error. Okay, so this is the basic of Gauss quadrature. But for this course, this will not be discussed in detail. Yeah, this will not be discussed in detail. So that in this case, for the integration for this course, yeah, so that the integration area, yeah, will be 4 method. Yeah, so there will be 4 method that is discussed in this course. Yeah, so we have trapezoidal. Yeah, we have trapezoidal, and then we have Simpson 1/3 rule, and we have 3/8 rule, and last is the Romberg method. Yeah, so these 4 are the main topic that is discussed in detail, while quadrature in detail. So I suppose that will not be included in the exam as well. Yeah. Okay. So this is for integration. All right. Any question? Okay. So I hope that is clear enough. Yeah. So that with this discussion last about Romberg method, so that will be the methods, yeah, that we have discussed. Now we will continue to differentiation. Yeah. Now before we just finish integration, now we also have differentiation. And when we talk about differentiation, we have learned about that as well when we learned about Taylor series expansion. Yeah. So remember? So that I will open the slide here. Okay, so now we continue on chapter 23, which is still in the same part, which is about numerical differentiation. Yeah, and we have learned of this before when we learned about Taylor series expansion. Yeah, so we will just do a quick review on that. Yeah, so this will not be long. Just to remind you that we have learned of this, and there are several schemes that are available. Yeah, there are several schemes that are available. Still, I think you still remember on this. Oh, why it's not working? All right. Okay. So you remember that we have the Taylor series expansion, yeah, in which we can approximate the value of fx1, fxi plus 1, in which we can approximate the value of fxi plus 1 that will be equals to fx f accent xi times h plus squared h over 2 factorial second derivative of xi plus and so on. Yeah, and then we can do truncation for this. Yeah, and the order of the equations will depends on how many terms that will be included in the formula. Yeah, so if you use less term, for example, like this one, we approximate fxi plus 1, that will be equals to fxi directly. Yeah, so this means zeroth order. Yeah, zeroth order approximation. If we use two terms, or that we use a linear line, so in this case we have the first order, and so on. Yeah, so it depends on the number of terms that is included in the calculation. So that we can also do the expansion backward, so that we have learned before that we have several methods, depends on which in which direction the expansion of the Taylor series is performed. Yeah, so that we can have the forward scheme. Yeah, still I think you still remember we have forward, backward, and central difference. Yeah, and we can use that to find, for example, the first derivative, the second derivative, the third derivative, and the fourth derivative. And also we have the order of accuracy. Yeah, so it means that we can have the selection of the scheme, which is forward, yeah, backward, or central. And we can find this to find, for example, the derivative. Yeah, the derivative can be first derivative, which is fx and x, or the second derivative, which is second derivative like this one, or the third, and so on, up to the nth order derivative. Yeah, and we can also have the order of the accuracy. Yeah, the order of the accuracy, regardless of the chosen scheme and derivative that we want to find. The level of accuracy here is also needs to be determined, whether we want to use the first order's accurate scheme, the second order, or higher order, for example, third or fourth order scheme. Yeah. Okay, so I think we have seen that example before, yeah? Is it correct? We have learned about this before?
Yes, ma'am.
Okay, so that we will do that quickly. And why we repeat this, yeah? Because we will later talk about ordinary differential equation, in which we will use again the numerical differentiation. Okay, so because we have learned this, so I will just do this quickly, yeah, as a review. So that if we want to use backward difference, it means that the derivative will be calculated by connecting that point with the point before. So moving backward, yeah, connecting to the point backward. So xi here, all of the value, the derivative at xi here is calculated by connecting that point with the point before. So that with xi minus 1 or xi minus 2 and so on. Yeah. Or we can also have the forward scheme. Yeah, so this is the derivation. I think we have also discussed this as well. Yeah, correct?
Yes, ma'am.
Yeah, okay,
Yes,
we
ma'am.
have discussed. Yeah, we have discussed this as well. So we can skip on that. So for the second derivative as well, we can also combine the equation. Yeah, for example, we have fxi minus 2 and we combine the Taylor series expansion to fxi minus 1. When we combine both equations, so that we end up with a new equation here to find the second derivative, in which this is also first order, because when we divide it with h squared, so this will be h to the power of 1. So this is first order accurate to find the second derivative. So this is called, this is how to calculate the second derivative using the backward scheme, because we use all points before xi. Yeah, backward scheme, which is the order of the accuracy is first order. Aside from that, we have another method now, which is the forward approach. So that it means, again, similar to before, we can find the first, the second, or the third derivative at xi. Yeah, so the point is finding the properties or the derivative at xi, but by connecting it to the point forward. Yeah, the point in front of it. So that now all of the calculation or the formula here using the points after. So I plus 1, I plus 2, I plus 3. So this is forward difference. And we can see here that with this derivation, from this derivation, we can see it clearly that the resulting in this case is first order. Yeah, with using this formula. And the third scheme is the central difference, in which we can find the first, the second, the third, and so on derivative. Yeah, by, if we want to find the value at xi, so the value here is found by connecting the point before and after. So you see here that we have xi plus 1, xi minus 1. Yeah, xi plus 1, xi, and xi minus 1. Yeah, so we connecting the points backward and forward together. Yeah, and how is the derivation? We can find the derivation or the steps to get this formula by combining two equations of forward and backward. Yeah, the Taylor expansion backward and forward. We combine together, we do subtraction so that we have the result here. Yeah, the result here will be of h squared. Yeah, so it means that this is second order error. Yeah, so with central difference, we see here that the lowest accuracy will be second order. Yeah, while for the forward scheme and backward scheme, the lowest accuracy is the first order. Yeah, okay, so this is the difference. And we can also further find another formula for the second derivative, which is also second order accurate. And if we want to have a higher order accurate scheme, we can also further use or manipulate the equations so that we have a higher order scheme. Yeah, for example, here we have the Taylor's expansion, the Taylor series expansion forward. Yeah, and then here we want to find, for our goal is to find the first derivative. Yeah, so we want to find the first derivative here. So we rearrange the equation here. Yeah, so we move that to the front, we move the other to the back, to the right hand side, so that here, if we want to increase it to higher order scheme, it means that we want to have here to truncate here. Yeah, so that it becomes second order. So h to the power of 3 divided by h, so that will be second order. It means we have an additional term that should be included in the calculation. So how to solve this one? So we can substitute it from the second derivative that we have in the equations for the first order scheme. Yeah, so that we see here that when we include the second derivative in the calculation using the first order approach, the same forward scheme, first order, second derivative, we substitute it here in the equations so that now we have the higher order forward scheme. Yeah. Now this is finding the first derivative, but this is second order. Yeah. Or we can have also for the backward scheme and center scheme to get higher derivative. Yeah. So that we can see here, we can find the first, second, and third derivative. Sorry. Using for higher order scheme. Yeah, so we see here that we can have higher order scheme, which is this is I plus 2, I plus 1. So this is forward scheme, yeah. Forward scheme, higher order scheme, which is second order, yeah, second order forward scheme to find the first derivative, the second derivative, and the third. And also for the central divided difference, this is for fourth order, yeah. So central divided difference higher order scheme, which is fourth order, because the lowest order for the central difference is second order. Now for the fourth order, here we have the calculation for the first derivative or the gradient here will be shown as this one. So we see here that when we increase the order of the accuracy, so that the dependency to the surrounding cell here increasing. Yeah, for example, here we have previously, if we want to find fx and x using backward scheme like this one, so that will be f x I minus fx I minus 1 divided by h. Yeah, so that will be the gradient, yeah, fxi minus fxi minus 1 over h. Yeah, so as we've seen before here, when we have first order, it means that one point here, when we want to find the properties or the derivative at one point, it will depends on one another point here before or after. Yeah, depends on the scheme. So that here we see when we use the backward scheme, yeah, backward scheme. But now, so this is first order. Now we have second order. Second order. So we see here that now we have to calculate the gradient at xi now depends on xi and also xi minus 1 and also xi minus 2. So it means that we want to find the value of here. Now it's not only depends on xi minus 1, but it also depends on xi minus 2. So when we increase the order of the accuracy, as well the number of dependency to the other points here increasing. Yeah. Okay. So this one as well for central difference, yeah. With fourth order, it means that now to calculate the gradient at xi, it depends on xi plus 1, xi minus 1, xi plus 2, and xi minus 2. So we see here that to calculate 1 point here, we have to include 4 surrounding nodes, yeah, 4 surrounding points, 2 points on the right and 2 points on the left. Yeah. Okay, so we will see the comparison here. I'm not sure yet whether we have discussed this before. Yeah, I'm a little bit forgot. Have we discussed this before? This example?
Not yet, ma'am.
Not yet. Okay. So we will compare several methods that are available. Yeah, several schemes such as forward, backward, and central difference here to estimate the first derivative of these equations. Now, actually, this is a very simple equations. Yeah, if you want to find the first derivative, so you can directly find the first derivative, which is minus 0.4 x to the power of 3 minus 0.45 times x to the x squared plus minus 1 x, yeah, minus 0.25, and then we can insert directly the position of x, yeah, in the equation. So directly we have the exact solution. Now this is just an example, so it's pretty simple, so that we can get the true solution for the first derivative. So the goal is finding the first derivative at x, which is 0.5. So this is the solution. Yeah. And here we want to compare with using different interval lengths. The first one is 0.5, so h value is 0.5, or the h value is 0.25. Okay, so first here we are going to use the forward difference. Forwards, it means that to calculate at that point, we connect that point with the point after. Yeah, so that if we want to calculate at 0.5, it means that we need to connect that with the point after, so plus 0.5. So that will be, yeah, with h 0.5 or the interval size of 0.5. So f accent at 0.5 is equals to f at 1. Yeah. So if you have 0.5 here, with h is 0.5, so that will be 1. Yeah. So that will be f1, yeah, f1 minus f at 0.5 divided by x, which is 1 minus 0.5. So the result here will be minus 1.45. So we see here that the error compared to the true solution will be 58.9%. So very large error. Yeah, very large error. Now we see here that we reduce the interval length. So that now to find the gradient here, we use h or interval size of 0.25. So that to calculate the gradient at 0.5, that will be equals to f at 0.75. So half of the size here, yeah, initially is h is 0.5, now is 0.25. So now the new value here is 0.75. Yeah, so f accent 0.5, that will be equals to f 0.75 minus 0.5 minus f 0.5 over delta x, which is 0.75 minus 0.5. And this is the result. Now the error here is 26.5%. So we see here that with the same forward difference scheme, which is this is first order scheme. Yeah, the same order of accuracy, but different interval size here. Different interval size. So we see here that the error, which is both is first order accurate, but now the error is dropped from initially about 59%, now becomes 26% by halving the size of the interval length. Okay. Next, we want to compare the result with backward difference. Yeah, exactly the same as before, but now we connect that point with the point before, backward approach. Yeah, so that with 0.5, that will be minus 1. Yeah, sorry, that will be minus 0.5. So that will be 1. Yeah, if that will be 0. Yeah, when we use h is 0.5, so at point 0.5, so that will be 0. So with backward approach, the first derivative at 0.5, that will be equals to f 0.5 minus fxi minus 1, which is f0, divided by delta x, which is 0.5 minus 0. So that the result will be minus 0.55. So the true error here is 39.7%. With the interval size, which is half of the initial, so that now we can calculate the gradient will be f 0.5 minus f half of it, so that will be here. So that will be f 0.25 divided by delta x, which is 0.5 minus 0.25. So the result here, the error will be 21%. So you see here that with backward difference, which is also first order scheme, yeah, both of these are first order, all of these are first order scheme. We see here now comparison between backward and forward. Yeah, backward and forward. The same order of accuracy, but first is using forward, 59% error. Using backward is 39.7%. So we see here that for this case, backward difference is more suitable. Yeah, is giving less error compared to the forward scheme. Yeah, in this case, but this is not always. Yeah, we have other cases as well in which forward difference can give better approximation. But in this case, for this curve, backward difference will be superior compared to the forward scheme. And again, if we see when we reduce the interval length with backward scheme, also the error is greatly reduced. Yeah, again, comparing the forward and backward, we see here that the backward scheme is still superior. Yeah, so approximately the same level of error, yeah, but a bit better using backward scheme. Now we will test it using central difference scheme, in which if we want to find the value at I, which is 0.5, so that will be calculated using the value of xi plus 1, which is 1, and xi minus 1, which is 0. So that the first derivative using h is 0.5. So that will be equals to f1 minus f0 divided by 1 minus 0. Yeah, so the result will be minus 1. So we can see here that the error will be less than 10%. So comparing to this one, the two of this, yeah, with the same interval size, yeah, with the same interval size, we see that central difference far better, yeah, with the error less than 10%. Why? Of course, because this is second order scheme, more accurate. Yeah. And if we further reduce to 0.25 for the interval length, we get now the error is even reduced, now becomes 2.4%. Yeah, so we see here that if we can choose, the best accuracy is to choose the higher order scheme. Yeah, commonly first order is not accurate enough. Yeah, first order is not accurate enough. So if you can aim to the second order, yeah, so that will greatly reduce the error level, so that you can get less than 10% error, yeah, with higher order. Next is to reduce the step size, yeah, or the interval size, yeah. So how to minimize the error? We can see here that the scheme, yeah, the scheme dealing with the scheme, which is the level of accuracy of the scheme, yeah, the level of accuracy of the scheme, we choose higher order. And then the second is use smaller interval length. Yeah, so if we use smaller interval length, so that the error is also greatly reduced. Next is the scheme. Yeah. What about the scheme? Which one is the best? In this case, we see that central difference is the best because it's higher order. Now, to define which one is the best, to make it fair, yeah, to make it fair, so we should compare it apple to apple. It means that we have to compare it with the same level of accuracy. So if we want to test the forward scheme, Yeah, if you want to test the forward scheme, so also test it with the second order forward scheme. Is also backwards second order scheme. So that we will try to test it. Yeah. So this is the equation that we can use. So this is tabulized in chapter 23. So you can see this in the book. Yeah. We have several formula, which is for the forward scheme to find up to fourth derivative and the level of the error here that you can choose with the first order error or the second order error. And also for the backward scheme here, yeah, so this is for backward scheme. We can choose we can find the first up to the fourth derivative with the error, yeah, first order and second order. And for the central difference as well, yeah, so this is for the central difference scheme, we can find the first up to the fourth derivative with the selection of error, we can be second order or fourth order. So that if we want to apply the same problem before, yeah, but now we want to compare at the same accuracy to central difference, which is second order scheme. Yeah, so that now we can calculate the first derivative using the second order scheme for the forward. Yeah, so this is the formula. So that will be minus fxi plus 2 plus 4 times fxi plus 1 minus 3 times fxi, and it's divided by 2h. So when we insert the value, this will be minus 0.8594. And also the backward difference scheme. Now this one, yeah. So this is also second order scheme. Yeah. And also we have this equation, which is minus 0.2 plus 8 times 0.6. So this will be taken from this equation. Yeah. So the last one that we tested here is this equation. Yeah. So minus fxi plus 2 plus 8 fxi plus 1 and so on. So we find the first derivative, yeah, which is fourth order. Yeah, over 12h. So this is over 12h. So we see the result here that it will end up here as the exact solution. Yeah. So we see here that using lower order scheme, yeah, as we seen before, which is this is the true value. We can compare that using the lower scheme or forward, backward, center. This is as before. This is using both 0.25 for the interval length size. Yeah, so that here for higher order scheme, second order accurate scheme, we have the error will be 5.8%. Backward scheme, approximately the same level. Yeah, second order scheme. So this is about the same as well. And now the error will become 3.77%. So if you compare here for the second order here, yeah, we see here that the central difference here is still better compared to the forward and backward. Yeah. While if you use the higher order central scheme, which is fourth order, this will yield to the exact solution. Yeah. So why this will yield to the exact solution? Because we see here that the equations is fourth order equation. So x to the power of 4. It means that if we use fourth order accuracy, so that will be the exact solution. Yeah, okay. So that will be yeah, so that will be the comparison, yeah, between three methods, yeah, with different accuracy level, yeah, and also we have seen the comparison with different interval size. Okay, is there any question here?
Maybe not, ma'am. It's all clear.
Okay. What about the others?
Still clear. Yeah.
Okay. Yeah, you can ask if you have any questions related to this. So the goal of learning numerical method, we have seen already, yeah, is to minimize the error, so that we have seen here that there are many parameters, yeah, that can affect the calculation, yeah. Uh, we have the order of the error, which is relates to the truncation error, yeah. We have also the interval size, yeah, in which the interval size here also has effect on the error as well, yeah. And be careful when we calculate for the interval size, yeah. Uh, we've seen here that if we reduce the step size or the interval length, yeah, we will have a more accurate result, yeah, more accurate result. But remember, if you make it too small, yeah, you make it too small, it means that the number of calculation will be more as well, yeah, will be more as well. So that will relates to the round of error as well. So if you have more floating point operations, yeah, there is a risk of an increasing round of error, yeah. And also for the selection of the scheme, it's not very clear, yeah, for each of the case which one will be the best, yeah. So how to choose for the best scheme usually is by testing, yeah, do some testing using forward, backward, on center. And later, if you learn about a more complex problem, yeah, you will see that there are certain problems that are more suitable using, for example, backward scheme, or there are some problems that are more suitable using center scheme. Yeah, so that really depends on the problem. For example, if you learn CFD later, you will learn that CFD in fluid simulations, the backward scheme is more preferable because of the stability on the calculation. Yeah. Well, perhaps if you learn about heat transfer, yeah, on a plate, for example, or you learn about structure, yeah, stress in a plate or a structure, for example, uh, the shear stress, for example, yeah. So that will probably using centered, yeah, will be uh, preferable because it will give a more accurate result, yeah. So which one of the scheme here, of the three scheme that we have learned here, which one is the most suitable for our problem, that cannot be determined easily, yeah. So you have to do some testing. And usually later we will also discuss about stability, yeah, the stability of the calculation later. So that is a more advanced topic, yeah. Probably, yeah, I think it's not discussed here, yeah, in this course, yeah. But later you will learn that numerical method will deal with stability as well as what we have discussed in the first few weeks, yeah. So the problem is not only error, it's not only about convergence, yeah, but also the stability of the calculation. Okay. Right, so this is a review on numerical differentiations. You have learned about this before, yeah? And we've seen just now here an example of comparing these schemes, yeah, and also the level of accuracy. Okay, so that what we've learned here, we will use that in solving differential equations, yeah? So I will continue to the next slide. So I will close this first. Yeah, so I will open a new slide here. Yeah, so we will continue to the next part in the book, yeah, which is about differential equations. Yeah. Have you heard about differential equations before?
In mathematics one.
Yeah. Yeah, I think you have learned in mathematics, yeah, about differential equations. So what is actually differential equation? We have learned about linear equations, yeah, linear equations before, a set of linear equations. Now we have differential equations. So what is the difference with that?
I think the in differential equation, the variable is uh, in the form of differential.
Correct. Yeah. So that is correct for that. Yeah. So when we talk about differential equation, because we have the derivative inside the equation. When we talk about linear equations, so that is a linear form. Yeah. It means that we don't have all will be of power of one. Yeah. So it will be a linear equation. But when we talk about differential equation, it means that we have a term in the equation in which it will be in the form of derivative, yeah, in the form of derivative. And this is very, very common in mechanical engineering. You have learned of many uh, uh, subject in mechanical engineering, for example. Yeah, when you learn about statistic, when you learn about kinematic or dynamic. Yeah, for example, the easiest one that we have learned before, when we learn about acceleration. Yeah, acceleration is actually the derivative of velocity in time. Yeah, so that is a differential equation, yeah, in which we have an equation which contains the derivative terms. So this is the example of the differential equations. Yeah. So again, this is the definition of differential equations. So when we have an equation which are composed of an unknown function and its derivatives at the same time. Yeah. We have an unknown function, which is phi, and we have the derivatives. Yeah, so this is called differential equations. Yeah, and we have many examples. So this is the easiest example. Yeah, we have seen this before. You still remember this in parachutist problem? Yeah, in parachutist problem in the first week. Yeah, in which this parachutist problem here comes from the balance of the Newton law. Yeah, sigma F is equal to m times a, in which we have the weight, the force here, we have the weight, and we have a drag force of the parachute. So this is because of the weight, and this is of the drag. So C here was the drag coefficient, yeah, in which this is simplified equations to make it easier. Yeah, so that A here, which is the acceleration, now written down as dv over dt. Yeah, the derivative of velocity in time. Yeah. So this is the simple equation in which this is called a differential equation. Now, for differential equations, there are two types, yeah, which is ODE and PDE. Yeah. So what is the difference of this? I think we have discussed this as well, yeah, in the first week, yeah, when we do an overview of this course. Yeah. You still remember what is the difference?
The difference is in parameter, ma'am. If ordinary differential equation is just one dimensional, and if PDE is more than one dimensional, is kind of two dimensional or three dimensional, maybe like that.
Yeah. Yeah, that is correct. Yeah, but it's not always in space. Yeah. So when we talk about more independent variables, so it's not necessarily always in x and y direction or in space. Yeah, but we can also have, for example, in time, for example. Yeah, so we have more terms. Yeah, and it's not necessarily always in space. Yeah. Okay, but it is correct. Yeah, when we have ordinary differential equation, it means that we have only one independent variable. Yeah, a function which is only have one independent variable. While we have PDE, we have two or more independent variable. So this is the example. Yeah, when we have ordinary derivative, for example, phi, in which phi here is only a function of t. Yeah. So then what is the derivative that is used? So we write it down as t phi over dt. Perhaps you have learned this in mathematics as well. Yeah, why this is different to del? Why we have different sign? This one is using t and this one is using del. Yeah. So del here is called as partial derivative. Why is it partial? Because it's not a complete representation for the derivative for the function. Yeah. So for example, such as in fluid mechanics, we have u, the velocity u, which is a function of x and y, for example. Yeah. So in this case, yeah, when we say the derivative in y direction, so this is not complete. We need another derivative, which is del u over del x. So why is used different symbol? Because this is to show that this is not a complete derivative for the function. We have other derivative in other direction or other variable, yeah, other independent variable. So this is called partial derivative. And later, yeah, because we have ordinary derivative and partial derivative, so that each of these will have an equation as well. Yeah, so that we will have ODE and we have PDE. Yeah. So when we have ODE, we have a function in which this contains ordinary derivative. Yeah, for example, here we have phi, yeah, in t, the derivative, and this is the second derivative. Yeah. So it's not necessarily the first derivative, but it can also be the second derivative. Well, for PDE, it means that we have the partial derivative in the calculation. So I think you made this before. In fluid mechanics, yeah, for example, you learned that we have like this one as well, for example. Yeah. So all of this is partial differential equations. Okay. So now we will focus on ODE, and later we will also learn a bit about PDE, yeah, and how to solve it. So if you look at this problem, yeah, perhaps this problem is not very easy to be solved mathematically, yeah, dealing with derivative. So that here we will look at ODE. We will see the type of ODE here. We already understand that it contains, it depends on one independent variable only, but the ODE can contain, for example, the first derivative or the second derivative as well. So that here we have x, which is the unknown function, and x here will depends on an independent variable, one independent variable, which is t. So that here we can have the first order ODE. Yeah. So when we talk about first order, dx. So this is first derivative. So this is called the first order equation. Yeah. So a first order equation includes the first derivative as its highest derivative. So we can have the linear or nonlinear form. And if we have the second order equations, this will include the second derivative. So this is the example. Now, if we have second order equations, means that we have the second derivative as the highest derivative in the equation. Or more, we can have third order, fourth order. It means that it will contain the fourth or the fifth derivative in the equation. So how to solve that, we will learn it later. In general, we can, if we have higher order equations, so that equations can be reduced to a system of several first order equations by redefining a variable. It means that we do substitution to a variable so that all of that can be split here, can be split or can be reduced to several first order equations. Now we will see about that again later. Okay, so we go back again in the parachutist problem. Yeah, in the parachutist problem, yeah, in which we have the physical law here, which is comes from the theory, and then we have the results, which is an ODE, and then we can solve it analytically using calculus or numerically here, yeah, using the solution. Okay, so we will take break for a while, yeah, for a moment, wait for a moment. So we will continue here, yeah. So if we have the mathematical equation here and we want to solve it, we can solve it using analytical, which is sometimes is possible, yeah. Sometimes it's quite easy, but sometimes can be quite difficult, yeah. So that we can use numerical approach in which we can replace the first derivative here with the numerical differentiation that we have learned before. Yeah. So for example, we use the forward scheme, which is first order. So that will be equals to Phi, yeah. When we approximate that one, yeah. So that will be, this is actually from the first derivative. So that will be, the first derivative will be Phi plus 1 minus Phi, forward scheme, over delta t. So with forward scheme, first order, so d phi dt, that will be equals to Phi plus 1 minus Phi over delta t. That will be equals to g minus c over m phi. So the value of phi here is taken at that time, that position. So that will be E, yeah, at the current time. So that we can find the value here, which is Phi plus 1. So we can rearrange the equation. So we move that to the right-hand side here. So that will be multiplied by delta t. And Phi moved to the right, so that will be Phi plus. Yeah. So this is actually to find Phi plus 1, yeah, a function of phi with time, yeah, using the forward scheme, which is first order. Yeah, first order forward scheme. Okay, so this is one way to solve for ODE, and this is using forward scheme. So this is called the Euler's method. Yeah, so this is called the Euler's method. Yeah, so this is the first method, which is called the Euler's method. Yeah, so with the Euler's method here, we have dy over dx, which is equals to a function of x and y. So we see here that we have the same one here. So we have dy over dx, that will be a function of x and y. Yeah, okay, so that we can solve for that. So that if we substitute dy over dx with yi plus 1 minus yi over h, so that we can move that h to the right hand side, so that will be fxi yi times h plus yi from the left, if we move to the right. Or we can say that if we want to approximate the value at yi plus 1 here, so this is the approximated value, so that can be calculated by yi plus delta, which is the slope, projected to h, yeah, so that we have yi plus 1 will be equal to yi plus the slope times the step size. So this is called the Euler's method. Okay, so we see here that if we have the true value here, as shown by this curve. So what will be the predicted value? So the predicted value depends on the slope that is calculated at xi. So then when we have this slope and this multiplied by h, so we can predict the new value will be here. So the difference between the predicted value and the true value, so that will be the error. Yeah, so this is the difference, yeah, or the error, yeah, between predicted and the true value. So this is the step. So this is pretty easy, yeah. So when we have this equation, for example, yeah, we see for another example here, in which we have dy over dx that will be equals to minus 2 to the power of x, 2 times x to the power of 3, yeah. And we have plus 12 squared x minus 20x plus 8 to 8.5. And we want to find the solution between x equals to 0 up to x equals to 4. Yeah, so that here we have the initial condition. Yeah, now we need an initial condition, which is for x equals to 0. So the y value will be equals to 1. So this is a condition that we need. So we need one initial condition here. Okay. And we want to solve it with a step size of 0.5. Okay, so we will use the Euler's method, in which yi plus 1 that will be equals to yi plus f xi yi times h. So this is the result. So we do time marching. Yeah, we do time marching, or we do marching from x equal to 0, and then with the step size of 0.5, we calculate for x 0.5 and so on. Yeah, so starting from one point here at 0, for example, and then we calculate the next value at 0.5, and then again with the slope that we calculated, we can again predict the value at 1. And then with the slope again, we can predict the value at 1.5 and so on up to 4. Yeah. So this is how the Euler's method is calculated. So we see here that when we want to calculate y 0.5, so the value at 0.5, that will be equal to y0 plus the slope. So this is the slope, yeah. So all of this here is fxy, yeah, which is the slope. Now here in this case, we only have that the right hand side here is only a function of x, so it's not a function of y. So when we have the x value, we can insert that directly. So this will be the slope. Yeah, so f01 here, which is at x0, y value is 1. So when we insert this in the equation, so it's only x value, so that will be 8.5. So this will be the slope. So at this point, the slope is 8.5. Yeah, for example, and we multiplied by the interval, which is 0.5, so that will be the value here, which is 5.25. So the value here will be 5.25. And then from this point, we project it again to 1. We do marching, yeah, to the next point. Again, at this point, so that will be y 0.5 plus the slope. So we insert the slope, the calculation of the slope, because this is the first gradient, the first derivative, yeah, the first derivative of the gradient is the slope. So we insert the value of x and y, because this is only a function of x. So we insert the value of x, which is 0.5 here. So we have this is the slope. Yeah, so this is the calculation of the slope times h, the distance, which is 0.5. So now we calculate the value of 5.875. So this is the point 5.875. And then after that, we do marching to 1.5. So this should be 1.5, yeah, not 2, but this should be 1.5. So we do marching to 1.5 again. That will be projected from value of y1 plus the slope multiplied by h. So what is the slope? We insert the value, the slope at 1. So we insert x is 1 and so on. Yeah, so this is the slope times the step size. So this will be the result. So this will be 1.25, for example, 1.125. Okay, and so on. So that with the complete graph here, so if the black line here, the black curve here is the true solution. So with using the Euler's method, yeah, using the Euler's method here, we have the result is here. Yeah, so which step size 0.5. Yeah, it means that we do the projection from 0 up to 0.5 and then to 1, 1.5, 2, and so on. We have the resulting here is the black curve with a dot line here. So this is the approximation, yeah, using 0.5. And when we reduce the step size now using smaller step size of 0.25, we see that now we have to calculate every 0.25, so that we have 0, 0.25 point, and then we have 0.5, 0.25, 0.75, and so on. So we see here that when we reduce the step size, yeah, so the error will be reduced as well. So we can see the difference, yeah, between the previous one using H 0.5 and using H 0.25. So we can see that also the error in this case is almost half. Yeah. So we see that reducing the step size in this case really help in reducing the error. But on the other hand, we should remember that the number of points that should be calculated in order to get the complete result up to x equals to 4, we need twice of the points from that compared at h 0.5. Yeah. Okay. So this is for the Euler's method. So that we can try to, for example, if we want to apply this method in computer programming, this will be very easy because we just need to repeat the instruction over and over from one position to another position. Yeah, so we do marching. Yeah, from t, for example, we have a step size of 0.01. We do marching from one to another point. For example, if you have 100 point, and don't forget to give an initial condition so that if we want to insert this in, for example, in MATLAB, so that we can insert this function as inline, we call it the function inline, and we insert the equation, so that will be 1 in single quotation, 1 minus 2 times phi squared minus t, and then we insert the variable, the parameter, we have t and phi, so this is the argument that is passed in the function. And then we define the step size, which is 0.01. And then we have the initial condition, which is at t0, the velocity is 1, for example. And then we store the information in array. So we have capital T and phi here as an array, in which the first element in the array is filled with the initial value. And then we do looping from t, from I1 up to 100. So then we do the calculation over and over, and we every time we do the calculation, and then we start to the second, to the next element in the array, so that we have a full array, and then we can plot the result. So we can plot t, phi, so that will be t, and this will be phi. So phi will be a function of the time. So this is the plot. Yeah. Okay, so this is the example of applying the Euler's method in MATLAB. So you can also do the same way. For example, if you want to apply this in Fortran or Python, yeah, more or less is similar. So you see there's in a form of looping, yeah, from one step to another step. Now, what if we have a system of ordinary differential equations? Before we have learned that we have a system of set of linear algebra, yeah, a system of set linear algebra. Now, what if we have a system of ordinary differential equation? So for example, we have several equations in which several ODEs to get to value, for example, of y1 up to yn. We have n equations of ODE to find n unknowns. So in this case, because ordinary differential equation is a marching problem, yeah, in which it's calculating from one point to another point. So in this case, it's quite easy compared to the set of linear algebra. So in this case, we don't need to calculate simultaneously, but we can calculate from one point to another point. So that here we can just calculate each equations as regular. So there is no matrix that needs to be composed, yeah, that we can just continue to the calculation, marching from one point to another point for each of the equation. Yeah, so this is more is simpler, yeah, is simpler compared to the set of linear algebra equation. So for example, here we have two equations of ODE. This is the first and this is the second, and we have two parameters needs to be found, yeah, the unknowns, which is y1 and y2. And we want to obtain the solution between x0 and 4 with the step size of 0.5. So similar to the previous question. Now, initial condition at x0, and this should be defined for the two variable that is not known, which is y1 and y2. So this to be provided for both unknowns. So how to find the solution? We still using the Euler's method, but we will apply the Euler's method for each of the equations. So we solve this for the first equations, yeah, so that we can find y1 first here, y1 at 0.5, that will be equal to y1 at 0, the initial step, yeah, y1 at 0 plus the slope. So the slope of y1 is this one. So we insert the value of minus 0.5 times y1. So y1 value, which is the initial value. So that will be 4. So minus 0.5 times 4 times h, which is the step size of 0.5. So the result will be 3. Once we finish with that, so we can continue directly to the second equations to find the unknowns. So that we have y2 at 0.5, that will be equals to y2 at 0 plus the function, the slope. So this is the slope for y2. So we insert the slope of y2 here now because this is depends on y1 and y2. So both of this value is taken from the previous step. Yeah. So this is the difference. So all of this value is taken at I. So it means that at the previous step. So that will be minus 4 minus 0.3 times y2, which is 6, minus 0. Times 4. So this is the slope times the step size, which is 8, that will be equals to 6.9. So we see here that we have the solution already. So we have two equations, two ODE, two unknowns, but each of these can be solved separately, yeah, in sequence, yeah, in sequence. So it means that we don't have to build the matrix. So again, we can calculate to 1 seconds, 1.5 seconds, x equals 0.5, x equals to 1, 1.5, and 2, and so on up to 4. So we directly get the result from this calculation. Yeah, so it's quite easy compared to solving a set of linear algebra equation. Okay, so I think that will be all, and we will continue again next week, yeah, which is about the other method to solve the ordinary differential equations. Yeah, we only learned about one method, which is the Euler's method, which is the simplest method. Yeah, so we will try to increase the accuracy of the Euler's method. There are several methods available, and we will discuss that next week, inshallah. Yeah. Okay, any questions for the Euler's method?
Maybe not for me. And the PowerPoint for these materials is still doesn't exist in classroom. May we boleh diminta nggak, Mem?
Yes, so I will upload this as well, yeah. So this is not uploaded yet. So inshallah I will upload it directly in week 13, yeah. So that will be for next week. So that will be the same slide for next week. Yeah. So inshallah, I will upload this. Yeah. What about for the previous slide? Is already uploaded there already? Sometimes I
Yes,
forgot.
ma'am.
Yeah.
Already, ma'am. For
Okay.
lecture 12, right?
Okay. So all is complete. Yeah. Complete except this one. Okay. Inshallah, I will upload it. Okay. And we will continue again next week. Okay. What about the others? Is this clear enough, or am I going too fast?
Excuse me, ma'am.
Yes.
I got a question.
Who is this?
Sorry
Aku?
for Josia, ma'am. Sorry, ma'am.
Yeah. Okay. Josia. Yes.
So, ma'am, sorry, but this is kind of out of topic, but I'm sorry, ma'am. I still haven't do the presentation because my classroom been lagging. When I go to the presentation at 10:08 or 07, there's already gone expired now.
Okay. What time did you join in? At 10?
I joined at 10:04, I think, because I need to go to toilet and I forgot to join at 9:50. So when I join, I already see the presence, but when I input, it's already got expired, man.
Okay. Right. Josia. All right.
Ma'am, and I have some question. For the presentation for what did it? For the 3rd November, it's still alpha, ma'am.
3rd of November. When is that? Last week?
2 weeks ago.
2 weeks ago. Okay. Yeah. It's when I run out of battery. Yeah.
Yes, ma'am.
So I forgot of that. Okay. I will take that. Yeah. Thank you to remind me. Yeah. Okay.
Again, you're welcome.
Yes. Okay. Yeah. Okay. Yeah. Any questions?
I think it's clear, ma'am.
Okay. Yeah. All right. So I will take on. Wait. Search. So I will check on the 3rd of November. So that will be 2 weeks ago. Yeah. 2 weeks ago. Okay, I will click on that. Yeah. Okay. Okay. Yeah. So I think that will be all for today. Yeah. So we will see again next week, inshallah, on the discussion of ordinary differential equations. And we are planning to have a project, yeah, a project which relates to the partial differential equations. So yeah, we will discuss that as well next week. Okay. All right. So that will be the end. Thank you. And wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Yeah.
Thank you, ma'am.